All right. So for today, we'll be talking about our first module, and our first module is about embedded systems. So what's in this class? We'll be talking about 8 points. The first one is Introduction to Embedded Systems, followed by CPU design, board design, actuators, control, sensors, image processing, and embedded software. In terms of embedded microprocessors and microcontrollers, CPU functionality, function units, structured CPU design, embedded system design, interfacing and integration, and the configurable computing. Under instrumentation, we have sensors, actuators, digital and analog input-output, motor drivers, shaft encoders, interface standards, and of course, the standard protocols. As for the programming for embedded systems, so we have assembly languages, C, C++, and interfacing with assembly languages, interrupt handling, timer interrupts, real-time systems, multi-threading, device drivers, data structures, and of course, programming techniques. In here, so you can see the illustration about embedded systems versus the standard computer systems. So we have here the CPU chip, and of course the microcomputer board that contains the CPU, the memory, and the interface, connected to the sensors, connected to actuators, real-time operation, and program once. So under the microcomputer board, we have the microcomputer system, example of which is the PC, printer, and disk drive. And of course, embedded system, example of which is the automotive application. So let's now proceed to the definition for embedded system. Basically, embedded system is a combination of hardware and software which together form a component of a larger machine. An example of embedded system is a microprocessor that controls an automobile engine, and an embedded system is designed to run on its own without human intervention and may be required to respond to events in real time. An embedded system is a specialized computer system designed to perform a specific task within a larger mechanical or electronic system. It typically includes a processor, memory, and input-output peripherals and is often optimized for efficiency and reliability. Examples include digital watches, home appliances, and medical devices. As per the application area, so this is the question that we needed to address. Where in our daily life do we use embedded systems? Here are explanations for how embedded systems are used in various consumer products. TV. Embedded systems control the user interface, channel tuning, video processing, and smart features like streaming services. Stereo. They manage audio processing, equalization, user interface, and connectivity options like Bluetooth and Wi-Fi. Remote control. Embedded systems handle signal transmission, button inputs, and sometimes voice recognition for controlling other devices. Phone or the mobile phone. They manage everything from the operating system, user interface, and connectivity that includes Wi-Fi, Bluetooth, and cellular to sensors and cameras. Refrigerator. Embedded systems control temperature regulation, defrost cycles, and smart features like inventory tracking and energy efficiency. Microwave. They manage cooking time, power levels, user interface, and sometimes smart features like sensor cooking. Washing machine. Embedded systems control wash cycles, water levels, spin speed, and user interface. Electric toothbrush. They manage brushing modes, timers, and sometimes connectivity to apps for tracking brushing habits. Oven or rice or bread cooker. Embedded systems control cooking temperatures, timers, and user interface, ensuring precise cooking. Watch. In smartwatches, they manage timekeeping, health tracking, notifications, and connectivity with smartphones. Alarm clock. Embedded systems handle timekeeping, alarm settings, and sometimes additional features like radio or Bluetooth connectivity. Electronic musical instruments. They manage sound synthesis, user interface, and connectivity options for recording or live performance. Electronic toys. Embedded systems control interactive features, sounds, movements, and sometimes connectivity for updates or new content. Medical home equipment. Devices like blood pressure, monitors, and thermometers use embedded systems to measure, process, and display health data accurately. PDAs. While more like standard computer systems, PDAs use embedded systems to manage the operating system, user interface, and connectivity options. Embedded systems are integral to making these devices efficient, reliable, and user-friendly. Here are explanations for how embedded systems are used in various application areas in the field of medical systems. So we have pacemaker, in which embedded systems control the timing and deliver of electrical impulses to regulate heartbeats. Patient monitoring systems, they continuously monitor vital signs like heart rate, blood pressure, and oxygen levels, providing real-time data to healthcare providers. Injection systems. Embedded systems ensure precise delivery of medication such as insulin pumps. Intensive care units. So they manage life support systems, ventilators, and other critical care equipment to maintain patient stability. Office equipment, such as printer. Embedded systems manage print jobs, control ink or toner usage, and handle connectivity options. Copier, they control the scanning, copying, and printing processes, ensuring accurate reproduction of documents. Fax, embedded systems manage the transmission and reception of documents over phone lines, converting them to digital formats. As per the tools, we do have a lot as well, like multimeter, in which embedded systems measure electrical properties like voltage, current, and resistance, displaying results accurately. Oscilloscope, they capture and display electrical signal waveforms, allowing for detailed analysis. Line tester, embedded systems check the integrity and performance of electrical lines and circuits. GPS, they provide real-time location tracking and navigation by processing signals from satellites. As per the banking, we do have a lot as well, like ATMs. Embedded systems handle transactions, user authentication, cash dispensing, and connectivity to banking networks. Statement printers, they print transaction records and account statements, ensuring accurate and timely information for customers. As per the transportation, so we have the following as well: radar. Embedded systems process radar signals to detect and track objects crucial for navigation and safety in planes, ships, and vehicles. Traffic lights. They control the timing and sequencing of lights to manage traffic flow efficiently. Signaling systems. Embedded systems ensure safe and coordinated movement of trains and other vehicles by managing signals and switches. Embedded systems are specialized computing systems that perform dedicated functions with larger systems. Here's a breakdown of their applications in various fields. Under automobile, so we have engine management, controls fuel injection, ignition, timing, and other engine parameters to optimize performance and efficiency. Trip computer provides information on fuel consumption, distance traveled, and other travel-related data. Cruise control maintains a set speed without the driver needing to keep their foot on the accelerator. Immobilizer prevents the engine from starting without a correct key or electronic signal, enhancing security. Car alarm detects unauthorized access and triggers an alarm to detect or deter theft. Airbag deploys airbags in the event of a collision to protect occupants. ABS, or the anti-lock braking system, prevents the wheels from locking up during braking, maintaining steering control. ESP or the Electronic Stability Program helps maintain vehicle stability by detecting and reducing loss of traction. As per the building systems, elevator that controls the movement, speed, and stopping of elevators, heater to regulate temperature to maintain a comfortable environment, air conditioning controls cooling systems to manage indoor climate, lighting automates lighting based on occupancy or time of day, keycard entries manages access control using keycards, locks control electronic locking mechanisms for doors, alarm systems monitors for security breaches and triggers alarms. And as per the agriculture, we have the following like the feeding systems that automates the feeding of livestock to ensure proper nutrition. Milking systems that automates the milking process, improving efficiency and hygiene. As per the space, we also have satellite systems that manages various functions of satellites, including communication, navigation, and data collection. Embedded systems are integral to these applications, providing precise control, automation, and enhanced functionality. In 1997, the typical US household contained more than 10 embedded computers. These embedded systems were integrated into various household devices, enhancing their functionality and efficiency. In 1998, embedded systems dominated the computing landscape, making up 90% of all computing devices, while traditional computers accounted for only 10%. This shift highlighted the growing importance of embedded technology in everyday applications. In 2001, the Volvo S80 model was equipped with 18 embedded controllers and two communication buses. These embedded systems manage various functions within the vehicle from engine control to safety features, showcasing the complexity and integration of modern automotive technology. Autonomous cars rely heavily on embedded systems to function effectively. The systems integrate hardware and software to perform specific tasks, enabling the vehicle to operate without human intervention. The following are the key components and functions. First is the sensors and data collection. So we have LiDAR that measures distance by illuminating the target with laser light and measuring reflection. Radar that uses radio waves to detect objects and measure their speed and distance. Cameras that capture visual information for object recognition and lane detection. And the GPS that provides precise location data for navigation. Number two, we have also the data processing and decision making. So we have the central processing unit or the CPU that executes instructions and processes data from sensors. The graphics processing unit or the GPU that handles complex computations, especially for image and signal processing. The artificial intelligence or AI, these are algorithms that analyze data to make real-time decisions such as obstacle avoidance and path planning. Third, we have the communication systems, under which we have vehicle to everything or the V2X that enables communication between the vehicle and other vehicles, infrastructure, and pedestrians. Internal networks that connect various embedded systems within the vehicle, ensuring seamless data exchange. And last, we also have the control systems under which we have electronic control units or the ECUs that manage specific functions like braking, steering, and acceleration, and actuators that convert electronic signals into physical actions such as turning the wheels or applying brakes. Applications in autonomous vehicles. So we have the navigation and mapping. Embedded systems process data from sensors to create detailed maps and determine the vehicle's position and route. Obstacle detection and avoidance, real-time data processing helps the vehicle detect and avoid obstacles, ensuring safe navigation. Adaptive cruise control maintains a safe distance from other vehicles by adjusting speed automatically. Lane keeping assist uses cameras and sensors to keep the vehicle within lane parkings, and the parking assistance that automates the parking process by controlling steering, acceleration, and braking. These are some of the challenges and future directions. So we have safety and reliability, ensuring that embedded systems can handle all driving scenarios safely. data security, protecting the vehicle systems from cyber attacks, regulatory compliance, meeting legal and safety standards for autonomous vehicles. Embedded systems are the backbone of autonomous vehicles, enabling them to perceive their environment, make decisions, and execute actions autonomously. Microcontrollers are essential components in embedded systems designed to perform specific tasks within larger systems. So what is a microcontroller? A microcontroller is a compact integrated circuit that includes a processor, memory, and input-output peripherals. Unlike general-purpose microprocessors, microcontrollers are designed for specific control applications and are often embedded within other devices. So these are the key components of a microcontroller. We have the processor or the CPU that executes instructions and processes data, memory that contains the ROM and the flash that stores the program code, RAM, temporary storage for data during operation, and the I/O peripherals interfaces for connecting sensors, actuators, and other devices. As for the types of microcontrollers, so we could categorize microcontrollers based on various criteria. First is the architecture. Under architecture, we have the hardwired architecture that separate memory spaces per program and data, allowing simultaneous access. Von Neumann architecture shared memory space per program and data. As for the data bus width, we have 8-bit suitable for simple control tasks, 16-bit that offers a balance between performance and complexity, and 32-bit that used for more complex applications requiring higher performance. As per the instruction set, we have the CISC or the Complex Instruction Set Computing, Rich Instruction Set with Complex Operations, and the RISC or the Reduced Instruction Set Computing that simplified instruction set for faster execution. As per the applications in embedded systems, microcontrollers are used in a wide range of applications including automotive, engine control units, airbag systems, and infotainment systems. Number two, consumer electronics, remote controls, microwave ovens, and washing machines. Industrial automation, we have the PLCs or the programmable logic controllers and robotic controllers. And number four, we have the medical devices, pacemakers, blood glucose monitors, and diagnostic equipment. Example, Arduino. Arduino is a popular platform for learning and prototyping with microcontrollers. It uses an easy-to-program microcontroller and provides a wide range of libraries and tools for various applications. Advantages of microcontrollers. Number one, compactness. Integrates multiple functions into a single chip, saving space. Cost effectiveness reduces the overall cost of the system, and efficiency optimized for specific tasks, leading to better performance and lower power consumption. Microcontrollers are the backbone of many embedded systems, providing the necessary control and processing capabilities to make devices smarter and more efficient. Read-only memory or ROM is a type of non-volatile memory used extensively in embedded systems. So what is ROM? ROM is a type of memory that retains its data even when the power is turned off. Unlike RAM, which is volatile and loses its data when power is lost, ROM is designed to store data permanently. So we have the key characteristics of ROM. Number one, non-volatile, retains data without the need for a continuous power supply. Number two, permanent storage, typically used to store firmware or software that does not need to be modified frequently. Number three, read-only, data stored in ROM can only be read and not written during normal operation. We have the types of ROM. Number one, masked ROM, programmed during the manufacturing process and cannot be altered. PROM or the programmable ROM can be programmed once after manufacturing. EEPROM or the erasable program ROM can be erased using ultraviolet light and reprogrammed. EEPROM or the electrically erasable programmable ROM can be erased and reprogrammed electrically, allowing for multiple updates. And the flash memory, a type of EEPROM that can be erased and reprogrammed in blocks widely used in modern embedded systems. We have different applications in embedded systems. Number one is the firmware storage, stores the firmware that controls the hardware of the device. Bootloaders that contains the initial code that runs when the device is powered on, initializing hardware and loading the operating system. Number three, we have the configuration data that stores configuration settings that need to be retained across power cycles. Number four, we have the lookup tables that used for storing fixed data that the system frequently accesses, such as character fonts or sensor calibration data. Example, the microcontroller read-only memory or ROM. In microcontrollers, ROM is used to store the program code that the CPU executes. This ensures that the code is always available and not lost when the device is powered off. Advantages of ROM: we have the reliability, in which data is retained permanently, ensuring the device can always boot up correctly. Security: since data cannot be easily altered, it provides a secure way to store critical code and data. Cost-effective: once programmed, ROM is a cost-effective solution for mass-produced devices. ROM plays a crucial role in embedded systems by providing reliable, permanent storage for essential code and data. Random access memory or RAM is a crucial component in embedded systems, providing temporary storage for data and instructions that the system needs to access quickly. So what is RAM? RAM is a type of volatile memory, meaning it loses its data when the power is turned off. It is used for storing data that the CPU needs to access rapidly during operation. Key characteristics of ROM: so we have the volatile data is lost when power is removed. Number two, fast access. Provides quick read and write access to data. Temporary storage used for data that changes frequently during operation. Types of ROM in embedded systems. So we have the static RAM or the SRAM, characteristics of which faster and more reliable than DRAM, but more expensive and consumes more power. In terms of usage, it often used for cache memory and small amounts of high-speed storage. Another is the dynamic RAM or the DRAM, characteristics of which slower than SRAM but more cost-effective and can store larger amounts of data, and commonly used for main memory in embedded systems. Applications of ROM in embedded systems: so we have data storage that stores variables, buffers, and other data that the CPU needs to access quickly. Program execution that holds instructions that the CPU is currently executing. Temporary data that is used for temporary data storage during computations and processing tasks. Example of which, microcontroller RAM. In microcontrollers, RAM is used to store the stack, heap, and global variables. It provides a necessary workspace for the CPU to perform its tasks efficiently. Here are the advantages of RAM. Number one, speed. Provides fast access to data, improving system performance. Flexibility: can be used for various types of data storage, from variables to program instructions. Efficiency: optimizes the execution of programs by providing quick access to necessary data. As per the challenges and considerations, we have the power consumption. SRAM consumes more power, which can be a concern in battery-operated devices. And in terms of cost, SRAM is more expensive than DRAM. So a balance between cost and performance is often necessary. Volatility, data loss, and power up requires careful management of data storage and retrieval. RAM is essential for the efficient operation of embedded systems, providing the necessary speed and flexibility for various applications. RAM and ROM contains a large number of memory cells per chip. The size of memory cell is usually 1 byte is equal to 8 bits. Size of RAM, example, 128K times 8 bits is 100K bytes. Note: the lowercase k is not equal to capital letter K. Smaller k is 1,000, but bigger k is 2 raised to 10, which is equivalent to 1,024. So the exact memory size is 131,072 bits. The size of ROM corresponds to number of address lines. So how many address lines are needed to access 128K? So 128K is equal to 2 raised to 7 times 2 raised to 10, which is equivalent to 2 raised to 17. Therefore, we have 17 address lines required. RAM or ROM chips always come in sizes of 2 raised to n bits. Let's break down how addressing works in embedded systems, particularly focusing on how the number of address lines determines the number of data cells that can be accessed. So, in digital systems, an address line is used to select a specific memory location. The number of address lines determines how many unique addresses can be generated and thus how many data cells can be accessed. Number one, if we have one address line, with one address line, you can have 2 raised to 1 is equal to 2 unique addresses. This means you can access 2 data cells. As for the two address lines, with two address lines, you can have 2 raised to 2 is equal to 4 unique addresses that allows you to access 4 data cells. For general case, with n address lines, you can have 2 raised to n unique addresses, therefore you can access 2 raised to n data cells. In embedded systems, the number of address lines directly impacts the memory capacity. For example, 8 address lines can address 2 raised to 8 is equal to 256 data cells. 16 address lines can address 2 raised to 16 or 65,536 data cells or 64 KB. 32 address lines can address 2 raised to 32 or equivalent to 4,294,967,296 data cells or the 4 gigabytes. This exponential relationship allows embedded systems to scale memory capacity efficiently by increasing the number of address lines. Each memory location contains one word, typically 8 bits or 1 byte, can also be 16 or 32 bits. Writing in one location does not affect other locations. As per the memory sizes, 1 KB is equal to 1024 byte, which is kilo and 10 address bits. 1 megabytes is equivalent to 1024 KB, mega, 20 address bits. 1 gigabyte or 1024 megabytes, giga, and 30 address bits. The number of memory addresses available to CPU is called the address space. Maximum memory size is equivalent to address space times the word length. Example, 8. Another example here is the 8-bit controller that contains 16 address bits, maximum of which is 64 KB memory size. Another example is a 32-bit controller that contains 68,332. 24 address bits addressing single bytes or 23 address bits addressing 16-bit words and the maximum of 16 megabytes memory size. And another is 27 address bits, 24 plus 3 function codes, maximum of which is 128 megabytes memory size. Let's explore how addressing works in ROM with 8 bytes of storage. Addressing in ROM with 8 bytes. In a ROM with 8 bytes, each byte can be uniquely addressed. Since 8 bytes require 3 address lines because 2 raised to 3 is equal to 8, we can use these address lines to access each byte individually. So these are how we address lines and addressing. Number one, address lines. The number of address lines determines how many unique addresses can be generated. Per 8 bytes, we need 3 address lines. Number two, address range. With 3 address lines, the address range will be from 000 to 111 in binary, which corresponds to 0 to 7 in decimal. Here's how the addressing works per each byte. Address 000 binary or 0 decimal accesses byte 0. Address 001 in binary or 1 decimal accesses byte 1. Address 010 binary or 2 in decimal accesses byte 2. Address 011 binary or 3 decimal accesses byte 3. Address 100 in terms of binary or 4 in decimal accesses byte 4. Address 101 in binary or 5 in decimal accesses byte 5. Address 110 in binary or 6 in decimal accesses byte 6. And address 111 binary or 7 in decimal accesses byte 7. In embedded systems, this addressing scheme allows the CPU to access specific bytes of data stored in the ROM. Each address line combination corresponds to a unique byte, enabling precise control over data retrieval. Dynamic random access memory or DRAM can be implemented using a single field effect transistor or FET and a capacitor. This design is known as a 1T-DRAM cell. Here's how it works. So we have the components of the IT-DRAM. Number one, transistor or the FET that acts as a switch to control access to the capacitor. Number two, capacitor that stores the data in the form of electrical charge. And in terms of the working principle, we have the write operation, read operation, and the refresh operation. Write operation, when writing data, the transistor turned on, allowing charge to flow to the capacitor. A high voltage or logic 1 or low voltage logic 0 is applied to the bit line and the corresponding charge is stored in the capacitor. As per the read operation to read data, the transistor is turned on again. The charge stored in the capacitor is transferred to the bit line. The sense amplifier detects the charge and determines whether it represents a logic 1 or 0. Refresh operation. DRAM cells lose charge over time due to leakage. Periodic refresh cycles are required to restore the charge in the capacitors, ensuring data integrity. As for the advantages of 1T-DRAM, we have the following: high density, only one transistor and one capacitor per cell, allowing for high density memory arrays; cost-effective, fewer components per cell, reduced manufacturing costs. As per the challenges, we have leakage and speed. Leakage, the capacitor loses charge over time, necessitating frequent refresh cycles. As per the speed, the need for refresh cycles can impact the overall speed of the memory. Example implementation: in a typical 1T-DRAM cell, the gate of the FET is connected to the word line. The source or drain of the FET is connected to the bit line. The other terminal of the capacitor is connected to a reference voltage, usually ground. Static Random Access Memory or SRAM is commonly implemented using a 6-transistor 60 configuration. This design is known for its speed and stability. Here is a detailed explanation of how it works. In terms of the components of 60 SRAM cell, it consists of the following: two cross-coupled inverters. Each inverter is made up of the two transistors, one NMOS and one PMOS. Two access transistors. So these are NMOS transistors that connect the cell to the bit lines during read and write operations. As per the structure, we have inverters and access transistors. As per the inverters, the two cross-coupled inverters from a bistable latch which can hold one of the two table states 0 and then 1. Access transistors, so these are transistors that are controlled by the word line and connect the cell to the bit lines for reading and writing the data. As per the operation, we have two, the write operation and the read operation. The word line is activated, turning on the access transistors Q5 and Q6, and the data is written to the cell by driving the bit lines BL and BL prime to the desired values. The cross-coupled inverters latch the new state. So that is for the write operation. As per the read operation, the word line is activated, turning on the access transistors Q5 and Q6, and the stored value is transferred to the bit lines BL and BL prime, and a sense amplifier detects the voltage difference on the bit lines to determine the stored value. As per the advantages of 60 SRAM, we have the speed, stability, and the low power. Speed, fast read and write operations due to the direct connection of the bit lines to the storage nodes. Stability, the cross-coupled inverters provide strong feedback, ensuring data retention. And low power consumes less power compared to DRAM as it does not require refresh cycles. As per the applications, 60 SRAM cells are widely used in cache memory, in CPUs and GPUs for fast access to frequently used data, embedded systems for storing critical data that needs to be accessed quickly, mobile devices where low power consumption and high speed are crucial. So this configuration is a fundamental building block in modern digital electronics, providing a balance of speed, stability, and power efficiency. As for the input and output, so as you know, it is required to communicate with the outside world. The PC system contains the keyboard, the monitor, the parallel port or the printer port, and also the serial port and the USB. As for the embedded system, sensors, example of which we have the automobile, we have acceleration sensor and the seat sensor. As for the actuators, in terms of the automobile, we have also the valves for the airbags. Input and output device implementation can be of the following as well: memory map, input-output map or the ports, and the direct memory address or the DMA. Let's explore the different methods of implementing input and output devices in embedded systems. Number one, memory map or the input-output, in which the same address space is shared between memory and input-output devices. Input-output devices are assigned specific memory addresses, and the CPU can read from and write to these addresses just like it does with regular memory. As for the advantages, it simplifies the CPU design as the same instructions used for memory access can be used for input-output operations. That allows also for more flexible and powerful input-output operations. As per the disadvantages, consumes part of the address space, reducing the amount of addressable memory. Example, accessing a display buffer or a network interface card or the NIC through specific memory addresses. Number two, we have the input-output map ports. In this input-output map or the I/O, also known as the port map I/O, separate address spaces are used for memory and input-output devices. Input-output devices are accessed using special instructions that are distinct from memory access instructions. So these instructions use port addresses instead of memory addresses. As per the advantages, it keeps the memory address space separate from the input-output address space, preserving more memory for other uses. Can simplify the design of the input-output subsystem. As per the disadvantages, it requires additional instructions and control logic in the CPU. Example, using in and out instructions in x86 assembly language to communicate with peripheral devices. And number three, the last, we have the direct memory access or the DMA. DMA allows input-output devices to transfer data directly to and from memory without involving the CPU for each data transfer. As for the implementation, a DMA controller manages the data transfer between the input-output device and memory. The CPU initiates the transfer by configuring the DMA controller and then can perform other tasks while the transfer is in progress. As per the advantages, frees up the CPU to perform other tasks, improving overall system efficiency, enables faster data transfer rates compared to CPU-driven transfers, and for the disadvantages, web adds complexity to the system design, requires careful management to avoid conflicts and ensure data integrity. Example of which, transferring large blocks of data from a hardware or hard drive to memory or from memory to a display buffer. In summary, memory map input-output uses the same address space for memory and input-output, simplifying CPU design but consuming address space. Input-output map or ports uses separate address spaces for memory and input-output, preserving memory but requiring additional CPU instructions. And last, DMA allows direct data transfer between input-output devices and memory, freeing up the CPU and enabling faster transfers. Each method has its own advantages and trade-offs, and the choice depends on the specific requirements and constraints of the embedded system. Thank you very much.